I'll ask you about some of those details, but since you're so busy with the hard engineering challenges of everything that's involved, are you still able to marvel at the magic of it all, of space travel, of every time the rocket goes up, especially when it's a crewed mission? Or are you just so overwhelmed with all the challenges that you have to solve? And actually, sort of to add to that, the reason I wanted to ask this question of May 30th, it's been some time, so you can look back and think about the impact already. It's already, at the time, it was an engineering problem, maybe. Now it's becoming a historic moment. Like, it's a moment that, how many moments will be remembered about the 21st century? To me, that or something like that, maybe Inspiration 4, or one of those would be remembered as the early steps of a new age of space exploration.
Yeah, I mean, during the launches itself, so I mean, the thing I think maybe some people know, but a lot of people don't know, is like I'm actually the chief engineer of SpaceX. So, I've signed off on pretty much all the design decisions, and so if there's something that goes wrong with that vehicle, it's fundamentally my fault. So I'm really just thinking about all the things that, like, so when I see the rocket, I see all the things that could go wrong and the things that could be better, and the same with the Dragon spacecraft. It's like other people say, oh, this is a spacecraft or a rocket, and this looks really cool. I'm like, I've like a readout of like, these are the risks, these are the problems. That's what I see, like so it's not what other people see when they see the product,
So let me ask you then to analyze Starship in that same way. I know you'll talk about in more detail about Starship in the near future, perhaps.
We can talk about it now if you want.
But just in that same way, like you said, when you see a rocket, you see a sort of a list of risks. In that same way, you said that Starship is a really hard problem. So there's many ways I can ask this, but if you magically could solve one problem perfectly, one engineering problem perfectly, which one would it be?
On Starship?
On Starship. So is it maybe related to the efficiency, the engine, the weight of the different components, the complexity of various things, maybe the controls of the crazy thing has to do to land?
No, it's actually by far the biggest thing absorbing my time is engine production. Not the design of the engine. I've often said prototypes are easy, production is hard. So we have the most advanced rocket engine that's ever been designed. Because I'd say currently the best rocket engine ever is probably the RD-180 or RD-170. That's the Russian engine, basically. And still, I think an engine should only count if it's gotten something to orbit. So our engine has not gotten anything to orbit yet, but it's the first engine that's actually better than the Russian RD engines, which were amazing design.
So you're talking about Raptor engine. What makes it amazing? What are the different aspects of it that make it, like, what are you the most excited about if the whole thing works? In terms of efficiency, all those kinds of things.
Well, the Raptor is a full flow staged combustion engine, and it's operating at a very high chamber pressure. So one of the key figures of merit, or perhaps the key figure of merit, is what is the chamber pressure at which the rocket engine can operate? That's the combustion chamber pressure. So Raptor is designed to operate at 300 bar, possibly maybe higher. That's 300 atmospheres. So the record right now for operational engine is the RD engine that I mentioned, the Russian RD, which is, I believe, around 267 bar. And the difficulty of the chamber pressure increases on a non-linear basis. So 10% more chamber pressure is more like 50% more difficult. But that chamber pressure is that is what allows you to get a very high power density for the engine. So enabling a very high thrust to weight ratio, and a very high specific impulse. So specific impulse is like a measure of the efficiency of a rocket engine. It's really the effective exhaust velocity of the gas coming out of the engine. With a very high chamber pressure, you can have a compact engine that nonetheless has a high expansion ratio, which is the ratio between the exit nozzle and the throat. So engines got, like, you see a rocket engine's got like sort of like a hourglass shape. It's like a chamber, and then it necks down, and then there's a nozzle, and the ratio of the exit diameter to the throat is the expansion ratio.
So why is it such a hard engine to manufacture at scale?
It's very complex.
So a lot of what does complexity mean here? Is a lot of components involved.
There's a lot of components and a lot of unique materials that so we had to invent several alloys that don't exist in order to make this engine work.
So it's a materials problem too.
It's a materials problem, and in a staged combustion, a full flow staged combustion, there are many feedback loops in the system. So you basically you've got propellant and hot gas flowing simultaneously to so many different places on the engine, and they all have a recursive effect on each other. So you change one thing here, it has a recursive effect here, it changes something over there, and it's quite hard to control. There's a reason no one's made this before. And the reason we're doing a staged combustion full flow is because it has the highest theoretical possible efficiency. So in order to make a fully reusable rocket, that's really the holy grail of orbital rocketry, you have to have everything's got to be the best. It's got to be the best engine, the best airframe, the best heat shield, extremely light avionics, very clever control mechanisms. You've got to shed mass in any possible way that you can. For example, instead of putting landing legs on the booster and ship, we are going to catch them with a tower to save the weight of the landing legs. So that's we're talking about catching the largest flying object ever made on a giant tower with chopstick arms. It's like Karate Kid with the fly, but much bigger.
Pulling something
this
like
probably
that
won't work the first time. Anyway, so this is bananas. This is banana stuff.